Now let's proceed to the fourth part of Lecture 8, namely graphs. So most likely we're not going to have enough time to cover this in class, but it's online anyway in case you want to know a bit about it. Mind you, there's no way that we can cover all of what's going on in graph neural networks within about 20 minutes. So this is really just enough for you to let you know that there's a huge field of science out there that's very, very active right now, and where if you have, relational data, you can probably build quite excellent models with much better tools than maybe a decade ago. So our graph of choice is going to be, the relationship graph between all of those very nice and honorable gentlemen. And you can clearly see that there's somebody at the center of a lot of this influence. And let's see how we can model this. So if you think about it, so we looked a lot at sequential dependency. So for instance, a time series, but in many cases we have more than just sequential. We might have spatial dependence. We may actually have spatio-temporal dependence, but for instance, with a road network, the fact that there's maybe a road going from, San Francisco all the way down to LA with various, cities on its way. So this is actually following El Camino Real. Well, that tells you that those cities are related, that their traffic's related, that maybe also if somebody gets sick in one place, COVID-19 and other things spread along those directions. Also good news, influence, and so on, they all spread. So you have spatial dependence. If you have drought, it affects regions. Likewise, on a social network, you may have a spread of fake news and of memes, or you might have a product recommendation graph where users purchase items, items are being sold by vendors, users leave reviews about vendors or about items, they buy them at a certain amount of time, there may be multiple vendors that sell the same item. So there's a lot of really rich relational structure there, and we may want to use it. As a rule of thumb, if you have a relational database, you can probably, and you probably want to model it as a graph. Now there are a couple of ways how you can express this. So first of all, well, you can't write it as a sequence, and one way to deal with that is, for instance, to write it as a directed graphical model. In that case, you write it as, set of, distributions of random variables given the parent of these variables. So in other words, for instance, if I have, two variables here, they are parents, then they may jointly influence that child random variable. So then the blue variables would, so if this is variable I, then the blue variables, let's call them J and K, and we would have that J and K are the parents of variable I. Okay. Now, this is nice when it works, but it's not always the case that a directed graphical model is an accurate representation. So in some cases, all you can really do is model correlations, and in that case, an undirected graphical model is a good idea. Mind you, these are not the only ways how you can model joint distributions over a lot of random variables. For instance, if you're interested in copulas, there's something called principal vines. Like in the vineyard, there's actually a very nice Annals of Statistics paper on that. So if you're interested in copulas, then, well, enjoy. Now, what can you do if you have a graph? Well, one thing you can do is you can try to regress on an edge. Or you can regress on a vertex. So regression on an edge, for instance, might be, talks to, or maybe arrests, maybe bribes, right? Or marries their daughter or their son or something like that. Likewise, you can regress on the vertex. Maybe you could have something like, whether they are corrupt or whether they are honorable, or, stuff like that. Or you can have, just finding out maybe there should be really an edge between those two gentlemen. Who knows? I'm not an expert in Russian politics, so you tell me whether this is a reasonable thing or not. Also, you may want to get feature embeddings like is currently in jail, or, well, what their roles are, what their future roles are. So you can actually perform a lot of really interesting estimation given such a graph. And you can possibly then predict what's going to happen given that interaction network. So if you want to do this maybe in a slightly less political science manner, you might want to use this for a social recommender, like on Facebook. Hey, we found those friends recommendations. And sometimes you may ask yourself, how on earth does Facebook know this? Well, what it usually does is it actually is able to look at maybe your phone numbers. You look at the graph maybe 2-3 steps out. It looks at, related interests, and then it recommends you people that you're not connected to, but that may actually have very reasonable related interests to you. You can also use it for fraud detection. So for instance, if somebody purchases stuff on Amazon and they're up to no good, then eventually, at least that's the hope, we will catch them such that they cannot do any more damage. So for instance, they might not be able to, sell some, fake keyboards, or they might not be able to, create fake returns of items. So there are a lot of interesting things that you can do. Now, all of those things you can do with graphs and then with some interesting algorithms on graphs. So in general, what I'm going to do is I'm going to refer to vertices V. So these are the circles in this graph. Then the edges are just the links between them. And you may want to, estimate additional vertex labels given, a subset of those labels, or given, some edge attributes, infer the remaining ones. And it turns out that a lot of this can be written through vertex updates. Okay, so the obvious plug here. And mind you, this idea is actually quite old. So there's this algorithm by Weisweiler and Lehmann from 1976. And it basically goes as follows. It says, well, a graph isomorphism is trivial if all the vertices have unique IDs. So overall, graph isomorphism is a hard problem. But if all the vertices were uniquely labeled, then you could easily solve the graph isomorphism problem. Right? So if I have, one graph like so, 1, 2, 3, 4. And this is my graph. And I have another graph here. Then, well, it's actually not entirely trivial how I map those two graphs to each other, because I could, for instance, map this vertex to that one, or I could choose to map this vertex to that one. So you can already see that symmetry and so on make isomorphism hard. But if, the green graph was also labeled and it would go like 1, 2, 3, 4, then you could easily see that out of the blue and the, pink or magenta version, the magenta edges are clearly the correct ones, because then we'll get this, we'll get that, and so on and so on, right? And this edge goes here. So that's the graph isomorphism problem. Now, if we don't have unique vertex IDs, what can we do? Well, it turns out that you can actually make them match up by just performing repeated hashing. So the idea is you start with maybe vertex ID 1 all throughout. One. And what we're going to do is we're going to write out a list of, vertices and also the IDs of the neighbors. So in the first case, we have 1 and then 1, 1. That's for the first vertex. For the second vertex, we have 1 and then 1, 1, 1. For the third one, we have 1 and then 1, 1 again. For the fourth one, we have 1 and then 1, 1, 1. Now in the next step, we go and hash those signatures for every vertex, and we get maybe a signature. Let's call the signature here 2, and here it's 3. It's 2, and here it's 3. And so now we get as the new signatures ones that are along the lines of 2, 3, 3. Then we have 3. Right, so this is one vertex, and then we have 3, 2, 2. Then we have 2, 3, 3. And we have 3, 3, 2, 2. And you can easily see that with this graph, it's actually not possible to solve the isomorphism problem because there is a certain mirror symmetry. Because if you now were to hash this up again, you'd only get, 2 distinct signatures. So up to those kind of symmetries, the graph isomorphism problem then is, solvable. And then, you can also see that, you want to terminate when stationary. So this idea was picked up later on by Shevarshytse and Borgward about 40 years later, where they said, well, okay, if we have this, then those vertex hashes are also good features. And then, the question is, can you prove equivalence to some graph kernels? And they did that, and it worked really well. Then when I saw their paper, I thought, okay, this is a great idea. Well, what about vertices with attributes? And it turns out that solving the problem of vertices with attributes was essentially unsolvable through manual engineering. So Nino, Karsten, and I spent a fair amount of time on that, and we failed, and there's no paper on it because it didn't work. Now, can we do something similar for PageRank, where again it's a vertex update? Because if you look at that closely, what we have here is we basically update the vertex state, so the vertex embedding, into a new vertex state. And in this case, it's just a simple hash. Now let's look at PageRank. So everybody remembers the random surfer model with restarts, where basically you start at the uniformly at a random location, you follow a random link at every vertex, and then with some probability you abort and you pick another random vertex to start with. And so what you get is that you get this very nice self-consistency equation. So the PageRank P of I is given by epsilon over number of vertices. So that's the random surfer part, plus and then 1 minus epsilon of just the updates, namely take all the incoming page ranks divided by the degree, and that's basically then the relevance of that page. So you can thus implement PageRank by running the local random surfer model at every vertex, where every vertex you just update its own PageRank based on the PageRank of its neighbors. Which is one of the reasons why at some point essentially high PageRank link spam became a thing, where if you had a reasonably popular web page, you would get emails like, can you please link to these and these pages and we'll pay you money for it. Okay. But again, it's a simple vertex update. So it turns out you can implement this fairly easily in DGL. So this is one of the deep learning on graphs libraries. And it's actually really straightforward. You basically have, a couple of states there. So you have basically the degree distribution. So n data is just, the data payload on the graph, and dig is just the degrees. And so I have basically first the need, let's just write this out. So we just have, PV basically goes into PV over degrees. That's the first step here. Then we perform an update operation here. So this is just defined as, send the message to all of its neighbors. And then the reduce function is just a sum function that is already, pre-configured. It's basically send it to the neighbors and also reduce everything. So if you will, this would be, here's the sum over all the neighbors. So that's really just, PV n and in the set of neighbors of some vertex I. And you then use this dampening term. So you basically, this is, what you get with, some epsilon, and here is 1 minus epsilon. So this way you make sure that the updates are smoothly calculated, and you iterate until you're stationary. Now, there's a similar pattern, again with vertex updates, that you can do for graphical models. And in graphical models, you basically have two things that you need to do. If this is, your graphical model, here we have, some cliques. So this is not necessarily any longer operating on single vertices, but on sets of vertices. And so if this is a clique, these are some other cliques, C prime, and maybe here's another clique that's called D. Then what you do is you can compute the clique potential by taking all the incoming messages, mu as in message, right, Greek M. Then you have the inherent clique potential, psi c, and you now take the product over all the incoming messages, right? Those are those guys here, times the clique potential, psi c, and that gives me the aggregate potential on that clique. Now, armed with that, I go and compute the outgoing messages, so those are the ones going back. And what I need to do is, I need to divide out the message that I've received from there, right? So this is basically my original phi c. And okay, so I get, phi c divided by mu d to c, because I don't want to send it the same message back that I've received. And then I need to sum over all the coordinates that are not relevant. So the bottom line being that this is effectively a vertex update algorithm, except that it's written on cliques of a graph as opposed to on vertices. Now, this is very nice if we can get, those functions, phi and psi. But if not, then, you need to learn them. And, a lot of really cool machine learning papers have been written about how to learn this efficiently. But the obvious question is, okay, can we just forget about the fact that those equations came from, graphical models and pretend that they were just simple update equations? As a matter of fact, if you do that, you can get a graph neural network out of that as well. So in short, well, if we didn't care about the graphical models and they may just converge anyway, can we learn this? So this was at the heart of a lot of the graphical models structure of what people did in the past. And so now the question is, these are vertex updates, can we learn them? And as a matter of fact, there's this paper by Kipf and Welling from 2016, which basically says, okay, well, if we have, vertex features, xi, and edge features, xij, we can go and compute new vertex and edge features using local update functions. And this is basically what's governed by these two equations here. So this second part is not in the Kipf and Welling paper. There's a DeepMind paper which essentially spells this out in great detail and says, okay, well, we can use edges too, but it's pretty straightforward once you have one then the other. So you run this for either a fixed number of steps, like this is what gives you like a graph kernel, Or you can run it to conversions like in PageRank, and this gives you two separate families of graph neural networks. And right now the jury is still a little bit out which one's better. There are very promising use cases and arguments for both. I would say right now this has a slight edge. I'm going to spare you walking you through the specific code because it's not going to be enough time anyway to go through that in great amount of detail, but I'll just quickly show you how this is done in general. So this is basically right now designing a one layer of a graph neural network. So this would be the equivalent of a linear layer in a multi-layer perceptron. And so what we need is we need to define both a message, namely sending the data to some other nodes, namely their neighbors. I need a reduction function which aggregates over terms. And then, well, this is exactly how you would design, just a linear layer. So you need, as a matter of fact, it derives from that, right? It needs input and output features, and probably by now you could actually use lazy tensor to do things a little bit more easily. So you would use lazy linear. Now the forward function does actually nothing else than, it takes all the inputs, it sends the corresponding edge state to along the edges, and also vertex states attached to it, through the messages. Then on the nodes, it aggregates terms, and then you get all the node features in the end by just requiring that throughout. And this is what this linear model does. So it's fairly straightforward. And if we want to design a two-layer graph neural network, then we just have a linear layer and have another one. So we introduce both of those. And then we just have the layer, we apply a ReLU, we apply another one, and that's the output. And so if I wanted to do that, for instance, for Zachary's karate network, then, I would happily, take 34 inputs because there are 34 participants in the network in 5 dimensions, and I instantiate the network as I would. Training it is entirely straightforward, at least if we don't do any sampling. And so all you do is you just really, so this could, for all intents and purposes, be just a standard, two-layer MLP graph code. The only reason why, this is a little bit more interesting is because, we have the detach here, and that's just to avoid further iterations, right? But other than that, you compute the gradient. So you reset the gradient, you compute it, you take an update step. This looks exactly like what you would typically do in a neural network. Okay. Now, back to the slightly more mathematical part. What you can do is you can also store state. And this is now very similar to the hidden state models in a sequence model. So remember there we had basically all the observed parts, and then we added some hidden state. And, in this case, you do that. Right. I'm too lazy now to draw the edges, but they always go forward in time. And now in this graph neural network, maybe you have, some graph, and then you have hidden state attached to that. And that hidden state may or may not interact with each other in the same form. So if it did, then you'd basically get that, right? Or it may not interact, but this allows you to store a more meaningful latent state than otherwise. Now, of course, it's only a question of time until people then also apply transformers to graph neural networks because, well, transformers work really well, and that's a good idea. Now, one minor twist, rather than, having to deal with a particular order in which you pool over your neighbors, you can actually pool in an arbitrary order. And there's a nice result on deep sets by Mansil-Zahir et al., which says that if I have a function on a set where thus the arguments in the set don't matter, I can then write the aggregation function as a simple sum. So that's quite important because it drastically simplifies the operations. Now, rather than having a nonlinearity of that sum, right, so sometimes people have, for instance, specifically encoded exponentiation and logs, and that gives you, for instance, hyperbolic graph neural networks. So this is a thing where you can then, get more meaningful updates on the functions g and f. And if you look at that, so you would probably look at Maximilian Nickel. And he's come up with, essentially a representation where we use logs and exp. And you can then give and rediscover fancy names for terms like Einstein sums and aggregations and so on. Basically, where you bring in notions from differential geometry into this. And yeah, it works. Now there's, as already promised, well, the ideas from regular deep networks bleed through into graph neural networks. The first thing is, graph attention. And the key point is really here that rather than having, an aggregation weight of 1, here you have an aggregation weight of alpha ij. And this is, for instance, given by this weighting function. There are other weighting functions that you can use because, well, any other weighting function in a graph neural network also carries over quite nicely here. And again, this works better on a number of data sets. Now, one of the cool things is that a lot of existing algorithms can actually be viewed as a special case of graph neural networks. So for instance, if you have a tree, then of course you can rewrite the tree as a graph neural network with the appropriate structure. And well, why would you do that? Well, because in many cases, for instance, for this, people have written fairly elaborate codes in order to do efficient computation there. Or you can just let your graph processing engine take care of all the issues, and then you don't have to worry about it. And as a matter of fact, that's what actually works just as fast and in some cases faster, because your generic graph processing engine can spend a lot more time on optimizing than what you would do manually. So this is one of those cases where automation wins against laziness of an engineer. You can do that also for transformers, and I'm not going to go into a lot of details on the transformer structure on the left. We'll cover that much later. But basically what happens is that everything depends on everything within a certain range, and then for the decoder, of course, you can do that, but always only moving forward one step at a time. So I apologize. Okay. Now, if you do that, you actually can get some nice benefits. So if you look at the aggregation function, right, so over each layer, you go and aggregate further and further and you get the output. Now, this is quite computationally expensive and it corresponds to a complete graph, or at the very least, a graph where every vertex has a very high degree. Now, what would you do if you have a vertex with a very high degree? You can often approximate it by a star topology where you add another vertex within that set, right? And then within that representation, you can actually quite nicely, simplify computation. And that, well, obviously, so the idea is really just, compare this to that. You can easily replace one by the other by just having that star. But now the number of operations is less than, is no longer quadratic, but linear only in time. And so you can actually easily perform this. And that works rather efficiently. So the sec-tree transformer is actually a lot less data hungry version, so you can do things in between. So rather than a star, you can have, some fairly efficient representation, and this works quite well. Now, there are a lot of tricks on how to make this practically useful. So for instance, you may want to only subsample over parts of the graph. You may want to learn how far to iterate rather than, performing an infinite number of operations. All of those things can be done to make this computation very effective. So for instance, what Dai et al. Did is they go and initialize compute updates, one vertex at a time. Then they take a regression loss where now you need to take care of two constraints. One is where you say, well, you want to have stationarity, so you want to make sure that you actually converge. The second thing is that your converged state actually be meaningful. And if you do that, you actually get fairly nice, self-consistent embeddings. Now, I know that this was quite quick, how I went through all things, but that's just because I wanted to mostly whet your appetite in terms of a lot of excellent things that can be done with graph neural networks. If you want to learn about that, so for instance, in Stanford, Yuri Leskovich is teaching a really nice class, I presume probably covering also GNNs. There is a lot of good tooling out there. So for instance, you can go to dgl.ai, and there are lots of examples and tutorials out there. There are usually workshops at NeurIPS and other things on graph neural networks. And with that, we covered everything that we want to cover in lecture 8. So we started with independence tests, went fairly deep in sequence models, and then in the end, now we talked about graphs. And with that, I hope that you enjoyed lecture 8.